this computer. Okay, so now I'm going to do speaker. Okay, so here we go. Get my little script intro. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, February 23, 2024. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool, overcast evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on Cape Ann's community access cable television channel hosted by 1623 Studios. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists, educators, and communicators around the world, far-flung friends, family, and other curious folk. Thank you for your active participation, comments, and general encouragements. Got to admit somebody here. Okay. For this episode, I'm happy to be hosting a longtime colleague, Dr. Sten Odenwald of NASA's Goddard Space Flight Center. Sten is an astronomer at Goddard and director of space math at NASA. He received his PhD from Harvard University in 1982 and has since been involved with investigations of star formation, galaxy evolution, and the nature of the cosmic infrared background. He has published over 100 technical articles on topics as diverse as star formation processes in the Milky Way, Big Bang cosmology, and the impact of severe space weather events on commercial satellite systems. He is an active science popularizer and book author and participates in many NASA programs in space science and math education. He has a number of websites promoting science education, including the Astronomy Cafe and Space Math at NASA. He also has appeared on National Geographic TV specials and other video documentaries. His most recent research involves chronicling the historic impacts of space weather on humans. In this evening's presentation, Sten will reveal the many mysteries of our nearest star, the Sun, and will take us on a brisk walk through all that the Sun touches, from its torrid core outward to interstellar space. So let's get going. The Zoom platform is all yours, Sten.
Okay, thank you. All right, let's share my presentation. It's all ready to go. Okay, well, I guess I'm just going to dive right in. Let's take a look at a little bit of a before and after. You know, to get a perspective on where we are, you know, it's kind of hard because, you know, every time we open a book or look at an article, we see these high definition images of the sun's surface, of planetary surfaces. You know, the Webb Space Telescope has revolutionized our infrared eyes. And we are being treated to sort of a veritable fire hose of high resolution imagery from literally across the universe. And quite frankly, as an astronomer, I find myself, you know, sort of mentally standing in front of a fire hose at full force. You know, you take a look at any of these images and you're just simply overwhelmed by the detail. And every detail begs a question about why does it look like that? But let's just take like the immediate past. If we look at this 1957 image taken with a 12-inch telescope on a balloon of a sunspot on the sun, you know, we can see it's got, you know, some good resolution to it. And that was the absolute best we could do back in 1957. But if you look at a simple image taken in 2002 with a 1-meter telescope with some interesting technology, I mean, it's high definition. You can see details in the solar granulation that's just quite mind-boggling. Resolutions all the way down to like 50 to 60 kilometers are possible with images like this. And at that resolution, you know, your models have to be not only precise, but they have to be ultra precise if you're trying to capture the general gist of what you're seeing in the image. And so that's a real challenge, you know, as an astrophysicist, to create models that are giving you information that has the same resolution and clarity as the kind of imagery you're now being treated to with your technology. Here's another one, which is a favorite of mine. On the left are the typical images that I used to see in textbooks in the 1960s of Mars, Jupiter, and Saturn. The image on the right was taken by the Hubble Space Telescope. Also, well, it's in orbit around the Earth, so it's at the distance of the Earth from these planets. And the resolution is just absolutely astonishing. And it's amazing that astronomers that were teenagers in the 1960s actually got interested in astronomy at all, because, I mean, look at the quality of the images they had to deal with, you know, interesting, but not inspiring for the most part. And so you had to work really hard to come up with interesting questions to ask with the very low quality data that you had. But, you know, there's a good side to that. When you have low quality data, you are forced to create theories which are broad enough to sort of capture what things look like at low resolution. So these theories generally include sort of the biggest concepts that relate to why the object looks the way it does, all right? As you get higher resolution data, you improve the theories because you can ask more detailed questions about why things look as they do. And that pushes you in the direction of, you know, more detailed theories, more tests that have to be performed, and so on and so forth. So there's this wonderful synergy that goes on between, you know, the progression of low resolution imagery to high resolution imagery and the progression of your knowledge. I mean, think of the images on the left at low resolution as being astronomers taken to what's the equivalent of grade school. Images on the right at that resolution are astronomers at the level of graduate school trying to understand what's going on. So it's a kind of an interesting progression in not only resolution of imagery, but also in the resolution of your theories to keep up with the image. Well, okay, our subject is the heliosphere. To get a sense of scale, from where you're sitting, the sun, for instance, might be a ball that's about 50 feet across. The edge of the heliosphere on that scale would be 120 miles away from where you're sitting. And about 30 miles away from where you're sitting would be Pluto. So that gives you sort of a scale of things. And of course, the Earth would be at about 1 mile away from where you're sitting. Of course, Mars would be 1.5 miles away, so forth and so on. So, you know, there's a lot of space out there, and heliophysics basically tries to describe sort of the general properties of the sun's influence, its non-gravitational influence across this vast span of distances. And luckily, we have a couple of spacecraft, the Voyager 1 and 2 spacecraft, who are basically well, they're not very good as eyes anymore. They stopped being eyes once they got past, you know, Neptune. But they have pretty good ears, and they've been able to hear all kinds of interesting things going on that theoretically we can then map into an understanding of what this most distant region of the Earth's the sun's atmosphere looks like. So that's all very good and very exciting. Okay, here's a kind of a dumb graphic that shows, I don't know, it shows a cloud erupting from the surface of the sun, and it shows the Earth and its magnetosphere in the upper right. And it's sort of kind of trying to summarize all the different phenomenology that we call space weather, which is basically the heliosphere of the sun acting up in a way that's not very beneficial sometimes for humans and human technology. So space weather is sort of the effects of heliophysics over the inner solar system. And it's something that we want to keep track of because we have a lot of technology and a lot of people in space. So we want to keep them safe and operating properly. And so we're going to start this exposition with the sun. And in fact, we're going to start in the core of the sun because that's sort of the basic powerhouse of energy for what goes on in the rest of the solar system. It's interesting when people draw diagrams of the interior of the sun, they often give the core of the sun, that brilliant white thing, a very hard edge. But in fact, it doesn't have that hard of an edge. It kind of bleeds off sort of like in a gradient way into the surrounding region called the radiative zone. It is blindingly white. In fact, its primary source of energy that you would see in the electromagnetic spectrum is basically gamma rays. These gamma ray particles, they're photons, they get scattered around by the nuclei that are present in the core. Every time they scatter, they lose a little bit of energy, and eventually they work their way out into the surface of the sun at very low energy, and then escape out into space, and we see the luminous surface of the sun as a result of that. We know a bit about the core of the sun because the general hypothesis is that the sun gets its energy from thermonuclear fusion. I mean, that's been established since the 1930s. And it's really neat that we have that idea because it turns out that it makes a specific prediction about something that we can measure from the core of the sun, and that's neutrinos. For a very long time, we couldn't detect these neutrinos at all very well until we developed the correct detectors to do that. But as a result, things like the Super Kamiokande detector in Japan has been able to track individual neutrinos coming from the sky, and they find that most of them come from a region surrounding the sun. And so by assembling all of these neutrinos together and identifying their directions, how they got into the detector and from what direction they came, can actually build a very crude picture of what the sun looks like in neutrinos. Now, this blob you see here is something like 10 times bigger than the actual size of the sun. That's because the neutrino detector has a very, very low ability to resolve details. But it's an outstanding confirmation that, yes, in fact, thermonuclear fusion is going on in the core of the sun as predicted theoretically. It produces exactly as many neutrinos as we're expecting to see. And you can use those neutrinos to confirm that the process is in fact going on. Now we get to an interesting concept. Well, how long does it take gamma ray light to get out from the core of the sun? Funny you should ask that question. I happen to have done a TED education talk on the very subject, and it's on YouTube if you're interested in pursuing this. It turns out that the way that light gets out from the core of the sun is it does a random walk sort of process. It takes a step in one direction, takes a step in another direction, and another, and the directions change randomly every time these gamma rays scatter off of the nucleus of a particle, of an atom or a particle that happens to be present. And so over time, it turns out that you don't wind up back at zero, back at your original origin, but in terms of the distance traveled from your origin, that number increases over time. In fact, it increases by the square root of the number of steps that you take. So you can actually work out a little bit. If you're a human being with a step size of 2 feet, to get to a distance of about 1 mile from where you started, you have to take about 7 million steps. If every step is a second long, it takes 70 million seconds or 80 days for you to random walk your way 1 mile from where you started. Okay. Now, that's not a preferred way of traveling, obviously. We're a little bit more clever than taking random steps all the time. But solar photons are pretty stupid things. They don't really know where they're going most of the time. And so for them, the average step size, sort of averaged over the entire volume of the sun, is about 1/10 of a millimeter. The goal is for that particle of light to travel to the edge of the sun, which is 690 kilometers away. And for that, it was going to take about almost 5 times 10 to the 23 steps. And at the speed of light, because that's how fast photons travel, That would take you about 52,000 years, give or take a few thousand. So even a simple calculation like this, using reasonably accurate parameters, says that sunlight takes tens of thousands of years to get from the core of the sun out to the surface. And then, of course, it only takes about 8.5 minutes to get to the Earth. So a photon of light produced by thermonuclear fusion in the core takes a while to get out from the center. And in fact, the ones that we see today started their journey 52,000 years ago, give or take. And that's long before humans, well, that's about the time when Cro-Magnon man was drawing things on cave walls in France. So that's about that sort of a time scale. Now, when most of the volume of the sun is actually taken up by this random walk process, we call that part of the sun the radiative zone. And it really is a substantial portion of the sun. About 20% of the inner sun is the core. You go out to about 80% and you get to the edge of the radiative zone. So 60% of sort of the radius of the sun is taken up by this random walking volume of the sun, which is at very high temperature and very dense. But nevertheless, it's a kind of a uniform region physically. Above that, the last 20% of the distance to the surface, you have what's called the convection zone. You can think of this as like, you turn on your hot plate on your stove and you put a pot of water on it, and then the water starts boiling. While the radiative zone is the hot plate, and the convective zone is the water in the pot that's convecting over to make your spaghetti or your soup or whatever you want to do. Similar kinds of processes go on with the sun, and it has a very active convective zone, which leads to some interesting processes. One of the things that happens is that, believe it or not, the inside, most of the inside of the sun rotates as though it were a solid body like the Earth. All the way out to the edge of the radiative zone, the interior of the sun is rotating uniformly at all latitudes. If you're standing on the highest latitude of the sun, it takes you exactly the same number of days to go once around as it does at the solar equator. But then throughout the convective zone, something bizarre, interesting happens. Basically, you wind up with the poles rotating slower than the equator. And in fact, what's going on in this whole zone is that the zone is actually robbing some of the spin of the sun and causing the sun to slow down over time. That process is mediated by the magnetic fields that happen to be there. And it's a kind of a magnetic braking effect. And magnetic braking is actually used in some cars and trains to slow them down very quickly. So magnetic fields can be used to actually slow down motion. And in the case of the sun, the magnetic fields that are generated in the convective zone are actually robbing, in physics, we call it the angular momentum, some of the angular momentum from the sun over time. The sun used to be rotating at something like 300 to 400 kilometers per second at the equator. Now it's only about 2. So it's slowed down by a factor of, over 200 since it formed. And all of that slowing down has to do with the activity of the convective zone and magnetic braking. When the sun started out a long time ago, it was extremely active magnetically. There were flares going on like nothing that we've ever seen since. And in fact, those flares produced huge amounts of not only solar wind, but X-rays and other things. And in fact, we can detect that kind of activity on other stars. We call them chromospherically active stars. They're generally very young. They're generally only about 10 to 50 million years old for stars of the mass of the sun. And it's a phase that is very violent early on, but then the star very quickly settles down into a more calm teenage and young adolescence, as you would call it. The other thing that happens is that in the boundary between the convection region and the radiative region, we have what's called the tachocline, and this is a region where there are shears that are set up, plasma moving in several directions at the same time. This causes currents to form, which then produce magnetic fields. So in this zone, which sits right on top of the radiative zone, we have the production of magnetic fields for the first time. But maybe not. There is some thought that perhaps the reason why the radiative zone of the sun is rotating the way it's doing as a solid body is because there's a leftover primordial magnetic field that permeates the entire interior of the sun. And this field is extremely stiff. It's numerically, it's about 1,000 Gauss units. And the sun, the Earth is only about a half a Gauss unit. So that's about what we're talking. And this very rigid magnetic field, the plasma that's trying to move in its own way is hamstrung by the fact that it has a very stiff magnetic field that it's tied to. So as the thing rotates as a solid body, it drags the plasma with it so that it also partakes of the same kind of motion. However, when you get up to the very tip top, just below the convective zone, some of that field gets distorted by the shears that go on there and gets converted into something that then pops through the surface. And that's why we wind up with sunspots. Now, what I've described is a kind of a hand-waving description of a very complicated physics, believe me. But the net result is that we wind up, as we're looking at the surface of the sun, with a star surface that is very active. It has sunspots, it has convection cells, it has flares, it has a variety of explosive activity. And none of that would be present if it weren't for the fact that the sun has a magnetic field. If it didn't have one, the only thing that we would see on the surface would be these convecting cells, like the ones you see in a pot of boiling liquid on your hot plate. And since one part of the surface looks pretty much the same as the other, it would be a very boring looking star. Fortunately, there is a magnetic field that's produced by this so-called dynamo process in the tachocline. And that allows magnetic field to be generated, to bubble up onto the surface and explode into a variety of phenomena that we see that gives basically the sun its character. In fact, without this magnetic element to the sun, we wouldn't have the glorious corona that we see during total solar eclipses. And we wouldn't see a lot of the other features that we've historically grown to admire, like sunspots, for instance. Here is an example of what happens if you take current image data from satellites like the Solar Dynamics Observatory, and you then try to map out mathematically what the magnetic fields would look like, given the information you have about the surface and sort of the details there. And so you see that the sun is very much of a hairy ball looking kind of an object. The red lines are north type polarities, the green lines are south type. You find that it's very complicated pastiche of some regions are north type and some are south type, and they're adjacent to each other. The adjacency of opposite magnetic domains can be a problem because magnetic fields like to contort themselves into their simplest shapes. And as part of that contortion process, they release a lot of energy. And that's why you get things like solar flares and coronal mass ejections. And also to a certain degree, why you get things like the solar wind itself, which is another important element of the sun and the heliosphere. Here is an actual photograph that's been processed in some considerable detail to bring out the details of the magnetic fields that are in the corona of the sun. And you can see that the magnetic field in the corona is very complicated. It's related to surface features. For instance, when the moon is not present, you can take an image of what the sun looks like very close to this very same time, and you'll see a variety of active regions whose magnetic fields you can map out, and they map pretty well into the streamers and plumes that you see in the corona. So we have a kind of a self-consistent picture of what the magnetic field of the sun looks like, we're still working pretty hard on trying to figure out the details of how it's generated at the tachocline, because unfortunately, the tachocline is hidden under 50 to 100,000 kilometers of overlying material. So it's really hard to see what's really going on there. You have to sort of infer it from the best physical theories that you have and their computational predictions. Here's an example of the active sun. I think this is supposed to rotate, and yes, it does rotate. It shows, not surprisingly, that the sun is a very active star, that magnetic fields are very dynamic objects that release energy, produce flares, those bright flashes that you see. And it's an interesting thing that we have a star that is so magnetically active that we actually can create very pretty pictures like this. If it weren't for that magnetic activity, this would be a very boring looking image indeed. Here's an example of what happens when magnetic fields interact and release energy. These erupting prominences, they tend to occur whenever you have opposing magnetic fields trying to merge together and reconnect into simpler shapes. They release a lot of energy. And very often the magnetic fields are loaded down with plasma. So when these explosions happen, they tend to release a lot of plasma into the upper atmosphere of the sun, producing these what are called erupting prominences. Many prominences, however, are very stable. They sit around for hours upon hours and seemingly don't move at all or change their shape very much. That's because they're in a very delicate balance between gravity, which is trying to pull the plasma down towards the sun, and the magnetic field tension within the loop, which is trying to push the plasma out into space. And if you get the amount of plasma just right, the temperature just right, and the amount of magnetic field just right, you can wind up with these suspended clouds of plasma in these prominences that sit around for a very long time. But unfortunately, like a pencil that's balanced on its tip, this situation is very unstable. And as soon as the plasma cools down just a little bit, the magnetic field gets the upper hand, and then you wind up with an erupting prominence, typically. I love these things. Here's another example of this. And this is the kind of detail that would be just absolutely amazing to anybody in the 1950s and 60s. I mean, they had some indication that there were flares and prominences and erupting features on the limb of the sun. But to have the kind of detailed imagery where you could actually map out individual magnetic field lines and how they're evolving to create the phenomenon, that is a very recent invention, which is only typically a few decades old. And it's allowed an enormous advancement in our theoretical understanding of how magnetic fields operate on the surface of the sun as dynamic objects, and what the consequences of that dynamism can be in terms of ejecting matter into interplanetary space, which is a highly important subject to be able to study, because as I said, those particles often wind up near the Earth, disrupting satellites, causing potential radiation hazards for astronauts working in space. So it's a good thing to have better models of what's going on the surface of the sun, because when you see something happening on the surface, you know what the predicate was for that phenomenon, and you can use that to predict whether or not something is going to happen or not. And that's really, in addition to just sort of the informational part of it and trying to understand the general activity of the sun, we're also trying to create essentially space weather forecasting tools that allow us to operate safely in space by looking at what the sun is doing at any given time and then extrapolating what it's going to be doing when an astronaut is doing an EVA, for instance, or a colonist is on the surface of Mars trying to do whatever colonists on Mars do. Here's an example of a coronal mass ejection. This is a powerful emission of a cloud from the corona of the sun. The cloud used to be magnetically suspended in the corona and fairly happy being there, but it got destabilized by one process or another and was eventually launched into interplanetary space. We can now follow this progression close to the photosphere of the sun and the inner corona and all the way out into interplanetary space, even as far as the orbit of the Earth. This is an absolutely wonderful way of seeing actual space weather events that can be a hazard to us. Now, if you take this particular coronal mass ejection, which is going sideways, it's not going towards the Earth, it's going kind of 90 degrees to where the Earth is in its orbit. If you rotate it around so that that coronal mass ejection is now directed directly at us, it looks very different. It looks like this growing halo of light surrounding the sun that then fades away. But then 2 to 3 days later, all of a sudden, the magnetic field of the Earth starts getting active and we wind up with aurora. This period of time between when it disappears as a halo event and reappears in the magnetic field of the Earth can last about a day or two. And that's kind of a disturbing thing because we don't know what the CME is doing during that intermediate period. And we'd like to have a better idea because that'll tell us how severe it's going to be when it gets here. But right now, all we have is sort of information about what it's doing when it's very close to the sun and before it really fades out. Here's another example. You start with an eruption of magnetic field on the photosphere of the sun. That eruption passes through the chromosphere and transition region and then winds up in the corona as a coronal mass ejection. I can watch this sequence, this GIF movie for hours. I mean, it's just fascinating to be able to finally see the origin of coronal mass ejections and the origin events for these phenomenal clouds of plasma. Again, they often happen when you have a very extreme, what's called an X-class solar flare. Lots of potential energy available, converting magnetic energy into plasma, temperature, and kinetic energy. And if that energy exceeds the escape velocity, the plasma gets launched into the corona and beyond. And so you wind up with a coronal mass ejection. Again, what we're seeing here is a coronal mass ejection that's sort of at 90 degrees to where the Earth is. So this is a harmless event that's never going to affect the Earth. It might affect Mars if Mars happens to be in that direction. And it certainly will wind up in the outer solar system because these things, they tend to go for months and months. Once they get started near the sun, they just continue propagating out to the edge of the solar system and beyond. In fact, the Voyager spacecraft was able to study many of these coronal mass ejection events all the way out past the orbit of Neptune and Pluto. And the time delays are basically what you'd expect in a coronal mass ejection traveling that distance from its launch time near the sun. Sun's magnetic field is very complicated. This is another amazing image showing the actual traceries of the magnetic fields near the sun and the transition region. Here is yet another image. This is a very curious image because you have complicated flares and features going on in the chromosphere of the sun. That's the upper part that you see here. You can see very filamentary features in the plasma. But then when you get to the edge of the sun, all of a sudden, you have this different pattern of behavior. You have these linear features. These are actually jets of plasma being ejected by the sun into interplanetary space. These have been imaged only in the last 5 to 6 years using SDO data and data from the Hanoti spacecraft and others. And what we are seeing here is basically the origin of the solar wind and the corona itself. These particles often travel with enough speed that they can escape the sun, and they carry enough mass in them to account for the mass that we see coming off of the sun as the solar wind. This is a a vast collection of particles streaming out from the sun at hundreds of kilometers per second. The destination of this wind, it penetrates through the entire solar system, out beyond the orbit of Pluto, and eventually winds up in what's called the heliopause, which is the boundary between the dynamics of the heliosphere solar wind and the dynamics of the interstellar medium, which is outside the solar system. So there's a kind of a boundary layer out there that forms as the high-speed material collides up with the interstellar medium. And so you wind up with what we call the heliopause. And that's about 120 times the distance between the sun and the Earth from the center of the sun. So on your scale model with a 50-foot diameter sun and the Earth at 1 mile, the heliopause would be out at 120 miles from where you're sitting. Here's another example of a coronal mass ejection that's actually tracked from the sun on the right, past Venus, which is that center blob, and arriving in the vicinity of Earth's orbit, which is the far left object. Of course, Venus and Earth are not shown to scale here. They're just identified as sort of a placeholder for the object itself, which would be unresolvable at this scale. But we're now able to use spacecraft like Stereo, for instance, to give us a side view of coronal mass ejections traveling through interplanetary space and actually arriving at Earth. And then we can compare that event with what we actually observe at Earth with Earth orbiting satellites to get a real comprehensive picture of how these coronal mass ejections, which we can now track in interplanetary space, how they actually affect the Earth's magnetic field. We can also gauge how strong these things have to be to produce observable, changes in the Earth's field. It turns out that in a spot that's about 1 million kilometers away from the Earth towards the sun, which on this scale is still pretty close to the Earth, it's only, as the crow flies, about 30 minutes away from the sun as a coronal mass ejection travels. We can actually measure the coronal mass ejection plasma and magnetic field 30 minutes before it arrives at the Earth's magnetic field. So we have some information, but ideally we would like to have space probes, all along the inner solar system, so we can track coronal mass ejections, from literally from moment to moment. Here's an example of typical high resolution space weather modeling of coronal mass ejections and the solar wind. The solar wind takes a spiral appearance because the wind is streaming out radially from the surface of the sun, but the sun is also rotating at 2 kilometers per second. So when you combine those things, you wind up with a spiral. It's called the Parker spiral, and it was discovered by Eugene Parker back in the mid to late 1950s when he started modeling the solar wind itself. And so you can see now that with the data that we have from coronal observations and from some interplanetary observations, we can actually start attempting to model using physics-based mathematics what the current space weather conditions look like and what might be arriving at the vicinity of the Earth at any particular time. These models often come into play whenever we have a coronal mass ejection that's spotted on the sun. They immediately gather the data, put it into the model, and then forecast what that particular CME is likely to do. And as I said before, most of the CMEs, they're going sideways compared to the direction of the Earth, and so they never arrive at the Earth. But a few of them do. In fact, about once every month, we have a good CME that arrives at the Earth and wreaks a little bit of havoc and produces brilliant aurora. A lot more of these during sunspot maximum and a couple of years after sunspot maximum. So this is actually the best time to be looking for aurora, starting about now. You should get a really good one every month or so. Here's another example of modeling what happens when coronal mass ejections encounter the Earth's magnetic field. Again, these are physics-based models. These are not animations by a graphics designer. What you see here is magnetic field of the sun being stretched and pulled as the incoming wall of magnetism from the CME passes by the Earth. It turns out that when the tail of the Earth's magnetic field gets pinched really badly, it basically snaps and particles flow into the polar regions to become the aurora, and then particles flow out in the opposite direction to become what are called plasmons. And these wind up all over interplanetary space. It's like the Earth during one of these events is sort of shooting clouds of plasma at Jupiter and the outer planets. Kind of an interesting process. The tail of the magnetosphere of the Earth stretches well beyond the orbit of the Moon. And in fact, there are lunar observations and spacecraft in, close to lunar orbit, kind of odd-looking orbits that, measure the properties of the magnetic field of the Earth's tail, and that helps us model these dynamic events. Oh, and I just noticed there's the Pleiades. I don't know if that was intentional or what, but you've got the Pleiades up there. Just happened to spot it. I don't really understand why they put the Pleiades in the background, because this is a dynamical model that has no stars in it. But, it looks lovely. Okay, and as I said, the particles from the tail that wind up in the magnetosphere of the Earth, near the Earth, they wind up producing the aurora that we see. And so we have a kind of a great description, literally from the cradle to the grave, of how solar activity on the distant sun can produce effects here on the Earth. And we can actually make models of where are good places to see a good aurora for any given coronal mass ejection that happens to come by. There are also other types of phenomena that produce interesting effects here on the Earth. Things like high-speed wind streams that come from coronal holes. There's also the solar wind itself, which isn't completely uniform, but is kind of broken up into sectors, and the sectors have different magnetic polarity, and these polarities can affect Earth's magnetic field, either, not affected or dramatically affected. But generally, CME and high-speed wind streams produce the weakest aurora, and it really is the coronal mass ejection events, these big solar storm events, that really rock and roll. And those are the ones that we try to predict as best we can. The solar wind, I just briefly mentioned it a couple of times. It sounds like, a wind, on a summer day, breezing up against your face while you're, sitting by the beach. It's nothing like that at all. Solar wind travels anywhere between 250 kilometers per second all the way up to 500 kilometers per second, whether there's an outburst going on or not. And, it's a collection of particles, generally ions, hydrogen mostly, and helium. But the problem is that these particles, they interact with planetary atmospheres. If the planet doesn't have a magnetic field, that's a really bad thing. In the case of Mars, Mars doesn't have much of a magnetic field. It's got a very lumpy one, but most of its atmosphere is unprotected by a magnetic field. So consequently, the solar wind smashes in to the atmosphere particles ballistically, and in many cases causes the particles to skip out of the atmosphere of Mars entirely. So the solar wind acting on a planet with an atmosphere which does not have a magnetic field is highly abrasive over time. And in fact, it's probably the essential reason why Mars has such a thin atmosphere today, because originally it didn't. It had an atmosphere dense enough to support liquid water on the surface. And it was also likely to be much more magnetically active than when it was very young. But over time, the core of Mars basically cooled and crystallized. The magnetic field went away. And over the next 3 to 4 billion years, you had this solar wind abrasion hammering the atmosphere of Mars, which probably was very Earth-like. Until now, it's only got 10% of its original mass, and that number is still declining. Problem is that Mars doesn't have any native volcanism, so it has no way of regenerating any kind of an atmosphere. In the case of Earth, we have a very strong magnetic field, plus we have tectonic mechanisms that keep producing volcanism to essentially recover any atmosphere that's lost. So atmosphere lost by the solar wind in the case of the Earth is very minor compared to what it is on Mars. And so this is an important thing. You know, if we're looking for exoplanets that are resembling Earth, we're going to need to find some way of determining whether they have magnetospheres or not. And I think in the case of one or two exoplanets, there is now a claim to have actually detected the magnetospheres of a couple of these exoplanets. Unfortunately, they're not terrestrial size. They happen to be gas giants, but you got to start somewhere. And so that's going to be an important clue as to whether or not that particular exoplanet, has an atmosphere that could actually sustain liquid water on the surface in reality. If there is no magnetic field, then you've got problems, and you have to construct evolutionary models for that particular planet and see which is the most likely. Yeah, well, okay, that's Mars. The solar wind eventually, as I said, finds its way out into the distant solar system, 120 or so astronomical units from the sun, or 120 miles from where you're located on this scale. And there we have a couple of things going on. We've got, first of all, the interstellar medium, and then we have the solar wind. And so the collision between these two is what produces what's called this boundary or bow shock wave, which kind of in cartoon language looks like this. The reason is that the sun is passing through an interstellar cloud that has been known by astronomers. We've known about this for several decades, and we've actually worked out some of the details of how the sun is moving relative to these local clouds. The sun happens to be located in what's called the local bubble, which is a void that's about 300 light years across, that probably was excavated by a couple of supernovae that blew up several million years ago, leaving behind this void. The void is actually high temperature plasma, but it's very dilute. It's only about 1/10 to 100th of a particle per cubic centimeter, compared to the regular interstellar medium, which is typically about 1 or 2 particles per cubic centimeter. So the sun is in a void, but that void is not completely empty. It's got little cloudlets, and we happen to be passing into one at this point. So it's not clear what's going to happen in the next 10 to 50,000 years, but things might actually get kind of interesting. And of course, the bigger picture is the sun is located sort of in the inner arm of the Orion Association, the Orion Spur. And of course, for you Star Trek aficionados, we can talk ad nauseum about how the galaxy is partitioned up by other civilizations. I kind of wish that this were the case, but we're never going to know that until we get out there. Anyway, that's it. Running a little bit late, but we started a little bit late too, so I guess all things are equal. If you're interested in more about the heliosphere, I encourage you to buy my book. We need a new roof, so I'd appreciate if you would buy as many copies as you could. That would be really nice and generous. Hopefully I can get a new roof in the next couple of years before it really starts getting rainy. But anyway, exploring the heliosphere takes you, is an ebook version and a color book, color illustration version. Tells you everything you want to know from the core out to interstellar space. And I'm sure you'll find some surprises hidden amongst the paragraphs. Anyway, so thank you very much. And if you have any questions, we can sort of move on to that segment.
All right.
I have a quick one, if that's all right.
So yeah, Mike, where are you? Well, there you are.
Yep.
Really quick, a CME. I was
Yes.
thinking about one sailing out past Uranus or Neptune. Do they dissipate like waves do at some multiple of the distance, or they hang together like a bullet?
They actually have quite a lot of integrity. What they look like, if you were to map out one, we think, is that they look like, remember the old Slinky that we used to play with?
Mhm.
Yeah, a slinky. Well, the magnetic field in a CME looks like the slinky magnetic field. It's kind of this cylindrical but helical kind of a field.
What do you
And
mean used to?
the foot points of that field are still located on the surface of the sun. But yet the whole thing has been so distended by the ejection of the plasma that the plasma has dragged this magnetic field out into interplanetary space. And also it's riding on the conveyor belt, which is the solar wind. So in most cases, it's seeing what looks like almost like a frictionless environment. So these CMEs, they can propagate sort of all the way out to the heliopause boundary, where they basically slam up against the interstellar medium, and then that's the end of them. But you know, we haven't actually imaged that whole process yet, but we have seen CMEs at least all the way out to the planet Neptune with the Voyager spacecraft. They've detected the particles and the fields that impulsively change as a CME passes. So we know that they are able to get out to at least 30 astronomical units, you know, still traveling at the speed that roughly they started out with. Of course, there's been a little bit of deceleration, but you know, still not bad.
Wow. So more like a taser shot than a shotgun blast.
I prefer less violent descriptions of my profession. Thank you.
Talking about the sun, it's violent to start with.
Ask a Martian.
It's doing the best that it can, you know? I mean, it was given a bad deck of cards with magnetic fields, and it's just trying to get through life, you know?
I'm amazed between neutrinos, photons, gamma rays, energy from the sun that we're not bombarded and wiped out the planet.
Oh, but there's so few of those. I mean, you get a trillion neutrinos going through you every second, even when you're asleep, you know, and I don't feel it, and you'll never feel it because they don't interact with you. So what's the harm, you know? Neutrons, a little bit of a difficult situation. If you're living in, you know, Denver, you got more neutrons coming through you than people on sea level, but they don't seem to mind up there.
Did a lot of travel by air. I was always impressed with that and seeing the aurora from an airplane.
Yeah,
Yeah, good stuff.
Didn't get rid of my
Bill Wall has probably a number of questions based on what was in the chat.
Aha.
Yeah, I mean, this was a really well done talk. I think you delivered this very well, and it was fascinating. I was fascinated through the whole thing.
I think it's mostly accurate too.
I have a couple of disagreements.
One
is, yeah, I mean, you calculated the length of time it takes for a photon to leave the center of the sun.
Yeah,
and that I'm afraid this is very popular. I've seen in the media. It only assumes a random walk, but there's more to it than that. As we know, the photons spend a lot of their energy time as thermal energy. Yep. So when you consider that, the thermal energy to photon energy ratio, modify that, it's 100 times longer, roughly, and you get like 30 million years, and it has to be that because that's the Kelvin-Helmholtz timescale. It has to be the same as the Kelvin-Helmholtz timescale because that's the timescale in which the sun would cool if nuclear fusion stopped. So it has to be the same.
The only problem is that it's fairly well understood that in the radiative zone you don't have any bulk motion going on at all. It's all radiative motion. So it's not like particles are moving outwards. The photon, now it's more complicated as you said. It's complicated because these collisions between the gamma rays and the particles, they change the energy of the gamma ray, shifting it down in frequency enormously.
Right.
But some of the collisions locally can increase the energy. So there's always this give and take. And basically what you should think of is sort of like this wave of photons leaving the core. It's not a single one. It's this wave of sort of a spherical wave going out from the center. And along that wave, you have photons that may have been born at roughly the same time at the core. but
Yeah.
they are not the same photons at all, as you say.
That's
They're,
exactly right. That's
they're,
exactly right.
you know, whenever you have, you know, two charged particles colliding with each other, they produce photons.
Yep.
And so
Yep.
the typical energies of those collisions in the outer core is probably, you know, 100 keV. It's not 2 MeV, which is the gamma ray energy. It's probably 100 keV is the particle-particle interaction. So you get photons typically at 100 keV when you get out, you know, to the outer core region. And,
Yeah.
and so
If
it's
you're doing
complicated, as you say.
yeah, I mean, if you do,
Yeah.
let's see, an order of magnitude calculation, I've seen this done before.
Yeah, I've done many of those.
It was the theoretical astrophysicist who did this, one of my professors. He did the random walk, and then he realized that he had to make this correction. And so what he did was just order of magnitude,
Yep.
thermal energy over photon energy, that increases by 100 factor of 100. Then you get the photon travel time being the same as the Kelvin-Helmholtz timescale, which is what you want.
But the problem is that these are not monoenergetic photons. That the problem is that at each distance you have a spectrum of photon
Sure.
energies, and each one of those energy bins produces a different, you know, Compton interaction cross section with the local particles. It's a complicated problem. But,
oh yeah,
you know, the estimate for 50,000 or 100,000 years is far better than 10 million, because the 10 million year figure comes from assuming that the entire interior of the sun is at the same density, which is the average density of the matter in the sun spread out over that volume. And then you get a mean free path from that, and you get a photon travel time at that mean free path, put it together, and you get, you know, and that gives you like 10 to 30 million years, which is obviously wrong, because there's a density and temperature gradient in the sun that has to be accounted for. The density gradient determines collision times. The temperature gradient determines the average energy of the particles, and therefore the Thomson cross section that you have to use, which is energy dependent. So, you know, yeah, I mean, I don't know what the number is. I don't think anybody's ever going to bother to calculate it, because it's not a number that
it would
really
be an interesting number to calculate exactly. Yeah, it would be interesting to calculate exactly, but yeah, I think it's more than 52,000 years though. And also, yeah, and
I think
also,
I'll leave it to you two to do the calculation.
Okay.
Yeah, I mean, one other
your
problem
longest
was
estimate and multiply it by take 50 million years, multiply it by 50,000 years, take the square root of that product, and you get up like a harmonic mean between two theoretical estimates. And that's probably closer to the true number anyway.
yeah, it could be.
Which is what we have in the textbooks.
Yeah, another
Right,
thing
which is a
that
million
there's this
years.
there's this idea that, you know, you need the magnetic field to protect you from the solar wind, and if you look at the ion loss rate from Venus, which has no intrinsic magnetic field, and Earth and Mars, they're all about the same. And I did actually read an article on this, and it said that, you know, having a magnetic field can make you lose your atmosphere faster in some ways for certain in certain cases, because the magnetic field will help pull off the ions from the atmosphere. So you can go either way. So
yeah, we have what's called the polar cleft. And whenever you have a strong CME, there's a lot of pumping of particles in the atmosphere out of the cleft into what's called the ring current. And primarily it's oxygen atoms, which is bad news. Now, those oxygen atoms come from the photodissociation of water vapor. So this is a way of pumping water out of a planet, you know, through a magnetic field, which is supposed to be protecting the planet. So.
all right, thanks.
Yep.
Paul Graveling has a question.
Yeah, hi. I wondered if you knew a woman I've heard of her named Tamitha Skov.
Say it louder.
Tamitha Skov.
Tamitha Skull.
Oh yeah, she's the space weather forecaster online.
Right.
Yeah. Oh, I really enjoy her products. They're
Yeah,
great.
the reason I mentioned it, I'm on her steering committee for
Oh,
the project.
yep.
And she's coming to Boston for the ham convention.
Ah.
And if you know, she deals with a lot of people, but if you told her who I was, she would know who I am.
Uh-huh.
I just wondered if you had ever heard of her. The really
Oh, yeah.
funny-
Yeah,
the really funny
I've
part-
exchanged a number of emails with her. Yes.
Good. And
Yep.
the really funny part though was when you pulled out the slinky, because she does that all the time. And
Really?
I wasn't sure whether she was crazy or if that was a good thing. I said, oh, this
Yep.
guy's got one too, you know.
Yeah, it's not bad. I mean, there are a couple of things that as someone that's not a heliophysicist really amaze me about this whole process. The first is that the photosphere of the sun is not a very good plasma. In fact, if you use what's called the Saha-Boltzmann equation for pure hydrogen at a temperature of 6,000 Kelvin, you find out that only one hydrogen atom out of 10,000 is really in an ionized state. So it actually is a rather poor plasma. But the prevailing comments that we always make in popularizing the sun is, oh, the surface of the sun is a plasma. That's why it interacts with magnetic fields. Well, it is a plasma and it isn't a plasma, but it behaves like a plasma that's very dilute, so. And the other thing is that the CMEs are still connected to the surface or the outer magnetic field of the sun through the foot points of the arcade that they represent. And I always thought that was really bizarre. Boy, these things really get stretched out, don't they?
Well, I have a question regarding sunspots. For quite a while, perhaps more than a decade ago, it was not clear how deep they go. And, whether they're like pothole covers or
Right.
they're deeply entrained into the interior of the sun. Has that been straightened out?
There's a thing called the Wilson effect. Basically, the center of a sunspot seems to be several thousand kilometers lower than the photosphere surface. But, the problem is when you talk about where surfaces are on the sun, you have to specify at what optical depth are you talking.
Mm-hmm.
And that's the problem, that the optical depth in the center of a sunspot, which is 2,000 degrees cooler, is different for the same density of particles as it is on the surface, which is 2,000 degrees hotter. So, the Wilson effect can be probably just accounted for not as an actual physical lowering of the center of the spot, but just basically the change in what you define as an optical depth of unity between the photosphere and the cool center. So I'm not really as well versed on sunspots as I would like to pretend I am sometimes, but I think the general sense is that if there is an effect like that as a physical lowering of the center of a spot, it's fairly minimal. But clearly it does represent some kind of an opening through which magnetic field lines are very highly collimated, like parallel straws or spaghetti that you grab. And that basically makes it very hard for plasma to move sideways and convect. So that causes the material in the center of a spot to be cooler because it can't convect the hotter plasma from the nearby photosphere into the spot to cool it, to make it hotter. So, that kind of information hangs together, and they can certainly model sunspots, magnetic fields in this way, and actually, the details of the outflow process that's going on. So, we've come a long way. But
any other questions?
I haven't got a question, but Sten, you should know that I'm looking at your face on a 65-inch TV, and I can see I can count your eyebrow hair.
I just bought a new camera 2 weeks ago. It's an HD something or other. And this damn thing is just a little bit annoying because my face used to be kind of fuzzed out so you wouldn't see wrinkles and stuff. But now it's like what you say, it's like.
I can count the pores on your face.
Well, thank you. I'm glad you have things you can do with your life at this point.
Well, I'm bored,
I mean, come on.
I'm retired. I got a lot of time on my hands.
Well, I've got a lot of pores, so
I can connect the dots. Hey, thank you very much. That was a very great presentation, and I hope you don't mind.
I appreciate it.
Yeah, thank you. I don't have a question, but I wanted to say thank you not only for the talk, but for the wonderful visuals.
Oh, great.
Yeah.
Nice.
Oh, yeah.
This fire hose thing actually got to me when I was preparing this presentation because I was looking for, some really good erupting prominence, imagery, in a GIF, sort of a format. And I realized there were just so many of these available that it's like, wait a minute now, we didn't have this kind of stuff available to us 30 years ago. And so I then sat down and thought, gee, we've gotten used to sort of unprecedented resolution and technology without even thinking about it. You know, and so I thought I would start this talk by just reflecting on, you know, how far we've come in only a few decades in terms of
It's
imaging.
visually impressive. Yeah, your talk was visually impressive. That's what I liked about it. Yeah.
Yeah.
One of the-
Oh, thanks. Yeah.
Well, the sun is kind of like too close for comfort. It's kind of like that high definition camera that you now have, Sten. There's so much you need to explain.
Out its pores.
Well,
right.
the more information you have about my face, the more I'm going to have to account for, you know, creases,
some-
pores, and graying, and
You can move back a little bit.
Some explaining to do.
oh, I'm kind of hunched over my desk here, sort of.
I can tell. There you go.
Well,
right.
he's studious.
All right.
All right. Well, thank you, gang. And thank you, Sten, especially. I reached out to you and you responded so quickly and so enthusiastically. And
Well, Bill, I don't have much of a life. I mean, I sit by the phone, wait for phone calls, you know.
an actor. All
You
right.
want to show off your pores? Yeah,
Well,
okay.
I think I'll stop the recording and let you guys go. Thank you
Okay.
all for coming.
Thanks so much.
Thank
Absolutely.
you. Have a great
Thank
Bye.
you, Bill. And thank you, Sten. That was amazing.
Thank you, Patty.
Thank you.
Bye-bye.
Bye.
Bye, Bill.
Bye-bye.